So this is just practice with the idea of model implied simple slopes, which we get to do in the longitudinal context today. So I have a model here where I have 4 predictors, F, G, H, and I, and F interacts with G and with H. And so given this model, how can you figure out what the model says the intercept should be and the slopes? So the first one here, write an equation for and then an estimate statement to get the predicted outcome for someone with these values of the predictors. In that case, you just fill in those values everywhere that the corresponding variable shows up in the equation. And the estimate statement then is given right here, where intercept is a 1, because you need 1 beta 0, you need 2 beta 1s, and so on. So, is that much good? Okay. Then the next one here, given this model, let me copy it, bring it down with us here so we can refer back to it. As you can see, I got tired of fighting with the online, or the, what is it, Canvas or Icon, whatever the hell it is at this place, and I'm just going to do it like this here. Okay, so write the equation for and an estimate statement for the predicted G slope for someone with an F of 2. So procedure, go up into the equation, find all the places where G is mentioned. So we need a beta 2. So we need one of those. So that's indicated here on the estimate statement. And we also need an F by G because the model says that the effect of F varies by, or the effect of G varies by F. And so that's beta 5, filling in the value for which you want the modifier to be 2F. Next one, then, get an F slope for somebody with G equals 3 and H equals 4. In this case, we need a beta 1 because there's the main effect of F. We need a beta 5, and we fill in the value of G that we want it for, and we need a beta 6, and we fill in the value of H that we want it for. And it looks like that. So, questions? No? And then the last one, write an equation for and then an estimate statement for the predicted I slope for someone with these values. Kind of a trick question, huh? Because what does the model say the I slope is? What kind of effect is this? Beta 4 here. It's a main effect. It's marginal. It's unconditional because I doesn't interact with anything. So I could say the predicted I slope for whomever, and it's still just going to be beta 4 according to this model. So all you would have to fill in is just 1 beta 4, and that's it. So, good? Good enough? All right. Then let's X out of that. So class registration has started. If you don't know already, I am teaching a clustered multi-level modeling course this fall. Even though you all are here right now, I would encourage you to take that if you can, because we're going to get further into multi-level models than we're able to do here because the time element takes up so much of our class time. The clustered models will get a chance to go into not only level 1 predictors, which we won't do this semester, but also models for outcomes that are not normal. So heading into sort of the intersection of where multi-level becomes IRT. So I would encourage you to sign up for that if you haven't already done so. I think you signed up, right? You're coming?
Yeah.
Yeah? She's like, no, it's going to be fun.
First, register first.
Yes, it's going to be fun. It's going to be very fun. But you know what other fun we get to have for today is start off with a review. So trying to put all of the steps together of what we've learned so far. This follows the appendix in chapter 6. It has kind of a flowchart sort of description as to what to do. So this is lecture 7A. This would be the process that I would go through anytime I'm handed a brand new longitudinal data set. So I have all of the steps summarized here on this front slide, and we'll go through them one by one. Okay. Ready? Okay, so lecture 7A here. So first model, first step 1, empty means random intercept model. In a nutshell, we fit this first to ensure that we actually have longitudinal data. So we calculate an intra-class correlation as a descriptive statistic. You can think of it in two different ways. One is that it is the proportion of variance in the outcome that is between persons at level 2 due to mean differences. And the other is that it is the expected correlation between occasions from the same person. So what value of ICC means game over? 1. That means you do not have longitudinal information, even if you have longitudinal data. Anything under 1, you're good to go. But the relative proportion of each is going to be prescriptive in terms of what types of predictors are going to be most useful. So in the data set that we've been working with the practice in response time over 6 sessions, the intra-class correlation in that data set was 0.82. So if I know that 82% of the variance is between persons, that means the most useful types of predictors will be between person predictors, level 2 predictors that are time invariant. That's what we're going to start talking about today. If most of the variation was within persons over time, then I would need time-specific predictors to account for most of the variability instead. Next step, something that we haven't focused on a lot but is often relevant in accelerated longitudinal designs, trying to figure out exactly what the metric of time should be. So this is a question that you have to think about from a theoretical perspective any time that people differ in the time metric that is supposed to be causing change. So when would that happen? If you have a sample of adults that you measure longitudinally where people vary in age at the beginning, then you have age differences at the beginning of the study as well as age differences as a function of time. Same thing if you sample kids at different grades and you follow them over time. If you're studying the effects of a new drug for treating some disease and the people that you are studying have had the disease for different amounts of time, so they would be in different points in their recovery. So anytime you have a situation like that, you have to think carefully about this issue. This is chapter 10, by the way, in the book, and something that I cover in the advanced version of this class that I used to teach. So once you have your time metric, you need to decide where time 0 is going to be. There is no wrong answer, but there are lots of weird ones. Somewhere within the data. A lot of times people put time 0 at the beginning. Sometimes people put it at the end. Some people put it at the mean time, whatever. But just keep in mind that that's going to be the reference point for whatever else happens in your model. And you can get predictions for other times besides 0 by asking for them as linear combinations of fixed effects, such as we do with estimate statements. Then it's time to get a sense of what the trajectory is like that you're trying to model. So saturated means model is the way to go here. That's the idea that we estimate a model in which each occasion gets its own mean, just for descriptive purposes. In homework 6, I'm asking you to compare how well your piecewise model is fitting the saturated means as an inferential, but even if you don't have balanced time, you still want to be able to do this just to be able to make a picture. So if people differ in their time schedules, I would round time into convenient intervals just for the sake of making this picture to try and get a sense of what the trajectory looks like. So is it linear or nonlinear? Is it continuous or discontinuous? That shape is going to guide you to which family of models for change is probably going to be most useful. Side note, the means that are in your data are not necessarily going to match the means that are coming out of the saturated means model. The latter assume missing at random. The means in your data assume missing completely at random. So to the extent that you have missing data, attrition, that kind of thing, the means will not match. But what the model is trying to recover are the saturated means. And so to me, that's the baseline that's most relevant, not the means in the data. So what if you have no change? Well, I have a continuum here of within-person fluctuation to within-person change, and the types of models that would fall under each of these categories. So on the left side, our designs where the outcome and the predictors fluctuate within people, things like mood and stress, but you're not trying to make them grow. There's no expected or found systematic effective change or individual differences in change. If that is the case, like the psoriasis example that we looked at, this is chapter 4, if time is pretty much irrelevant, there's no change, then the model for the means may not need anything in it to handle change over time because there is no change. The model for the variance would likely use alternative covariance structures, probably with a random intercept and those kinds of things. We have a special visitor today. What's the baby's name?
Mustafa Kemal. You can just say Mustafa.
Mustafa?
Yes.
Okay.
I'm sorry.
Yes, no, I have to go see the baby.
Let's see.
Hey, sweetheart. Oh my goodness, you're adorable. Are we gonna learn some statistics today? Yeah, we are. It's gonna be awesome. Yeah. So glad you could join us. Let me know if you have any questions. Yes, we all gotta come see the video.
Oh, I miss those days. Yeah. You can come hang out with me if you want to, buddy. So yes. See, now I'm going to lecture in my mommy voice. You know, when you become a parent, you adopt different voices, right? And the mommy voice talks like this. Alternative covariance structures is what we would use if we have within-person fluctuation. Yeah. Yeah. It's like I'm conditioned, you know, to like, it's just coming out of me. Anywho, yeah, so that's chapter 4. Chapter 6, on the right-hand side, when the study is designed to capture change over time. So change is expected and observed. That's where we have fixed effects of various kinds to capture average change, and we want to know which of those effects needs to be random to capture individual differences in change. In the middle is designs in which you're not really sure, where time was not supposed to be relevant, but it is, or which it was supposed to be relevant, but it's not. And you can do hybrid types of models. So for instance, you might need just a fixed linear time slope for average change, but then have a random intercept plus an AR1 residual, something like that. You can mix and match. So these families, you should just think of them as options that you can dive into whenever you need to. So there's not a single right answer most of the time. It's just trying to capture the means and capture the variances and covariances. So then if we have systematic change, we would go through the process that we did in Chapter 6, Example 6. Based on your pattern that you see in the saturated means model, and preferably unstructured variance model to get a sense of that too, you can try out different fixed effects, figure out which of those need to be random. You're building the model focusing on G, level 2 variance components. Then you would end up with something like this, where, for instance, if I have individual differences in linear change, that means I have 2 kinds of level 2 variances to be predicted, between person intercept, between person linear slope. Time invariant predictors is what's going to predict those, capture those. Level 1 then residual variance is why are you off your line today? Level 1 time varying predictors capture that. We're not going to get a chance to talk about those, but in a nutshell, level 1 time varying predictors almost always need to be treated like level 1 outcomes. So we're really talking about multivariate models in those situations. That's a whole long topic that unfortunately we won't get a chance to talk about this semester. But I do have plenty of resources in the rest of the book if you're interested in learning more about that yourself. If there's no systematic change, we may or may not need any random effects. Maybe just an intercept, maybe not. We may not need anything in the model for the means for time. So whether or not we have a level 2 random intercept or we just have some other kind of structure in the R matrix that doesn't have an intercept, that's okay. We can still test the effects of whatever kinds of predictors that we want. Yeah, don't you worry, bud. We can still test all the predictors. Yeah.
He's laughing.
Good. Yeah, I know. Isn't this stuff cool? Mm-hmm. Yes. So why is it that this is what, week 10 of the semester, 11, something like that? And we're just now getting around to putting in predictors? Here's my reasoning. Time is a really big deal to get right. It's very different than in multi-level models for clustered data where there is no time effect in which you can jump straight into predictors. But in this case, there is an order because what happens with respect to time dictates what is going to be allowable in terms of adding predictors. So if we start at the top here, first thing we enter are fixed effects of time. Those fixed effects are the anchor points, are the averages around which the random effects vary. The random effects then form the variances that person level or level 2 time invariant predictors are going to account for. And therefore, the effect of those person level predictors are going to be specified as a function of the time effects that are already in the model. So we know, for instance, if we have a random linear time slope, that putting interactions with time is going to be important in trying to capture that type of variance. Once we have our time invariant predictors, time varying predictors, then we'll pick up what's left. All of the time-specific variance that's not already accounted for in the level 2 model. And so that means that what fixed and random effects of time you put in the first place in the model dictate essentially what the rest of the predictors have to do. Time has to be handled first. So even if it's not your primary research question, because it's such a huge part of the design, it has to be handled first. Otherwise, all of the inferences that you may have after that may be suspect. Ta-da! So then just a couple reminders on how you would go through modeling strategies for polynomials and for piecewise. We did a whole lot of practice with that, so I think I don't need to belabor that point. So, questions? Any questions, baby? Are you okay?
Do you want to ask him a question? He has to. He asked, but I cannot answer.
Yeah, you want to get to predictors? Me too, bud. Let's do that. Yeah. He's like, I'm bored. You already covered this. Let's do that, shall we? Let's talk about predictors. Lecture 7B. So first, some bad news with respect to missing data and then the predictors. So, missing predictors. You're not going to like this part. So, have you heard the phrase that multi-level models handle missing data? You heard that before? Do you know what handle means? Handle means is something that you say when you don't know what you're talking about. That's what handle means. It's wonderfully vague. It's handled. How does it get handled? And so when people recite this to me, they are unpleasantly surprised that multi-level models do not handle missing predictors. They handle missing outcomes. So longitudinal studies often have some degree of missing information either in the predictor side or the outcome side. Even in techniques that use imputation to try and fill in the values that are missing, the goal is not to fill in the values. The goal is to maintain correct inferences despite the missingness. The goal is to get the right answers. And any method that you use to do that in the presence of missing data requires some sort of assumption about the missingness process as well as the variables' distributions. So what not to do, and I'm guessing I don't have to belabor this point with this group. Never, ever, ever fill in a missing value with a single number. You know that, right? Single imputation, mean imputation, single regression imputation, any of the things that SPSS or other programs will happily do for you if you ask? No, you can't make up data. List-wise deletion is also something to be avoided when possible. But the bad news is that sometimes it will happen in these models, and the way to get around it is not universally applicable. So what to do instead? There are two main things that people do to estimate models that include cases that have missing data. Full information maximum likelihood is one, known as FIML. By the way, is REML full information too? Do you remember? Remember we have ML and REML as our estimators? REML is full information, yes it is, but for reasons that escape me, FREML is not a thing, but it should be. So if FIML is a thing, FREML should be a thing. That's what we're doing in ProcMixed. It's using all of the available data, not just a summary thereof. So that's what full information means. Limited information is when you use a summary of the data to estimate the model, such as a polychord correlation matrix in the world of IRT. That's limited information. You can also do something called multiple imputation. Have you guys heard about this before? Yes? Yes, he probably hasn't, but that's okay, because you know how many times in my life I've done a multiple imputation? Anyone want to guess? 0. 0. It is unnecessary. Why? I'll tell you that in just a minute. So categorizations of missing data, you guys have heard this before, I'm assuming, right? The three main classifications of missingness. Missing completely at random, what it sounds like. Missing at random is conditionally random after you put stuff in the model that's supposed to be related to the missingness. Missing not at random, which is Are any of these testable? Are any of these empirically testable? You don't know?
I don't think so.
You don't think so? Only the first one. Missing completely at random is testable because if you find something in your data set that is related to the missingness, by definition, it's not completely at random. That's the only one though. And so missing at random is something that all of these missing data techniques assume. The bad news is that it is not testable. So this is something that reviewers love to harp on. Well, how reasonable is missing at random? Can you provide a test for it? No, I can't, because I am missing the data that would be needed to test it. What you have to argue with is saying that you've tried to put into the model all of the logical causes of the missingness or things it would be related to, so that you're conditioning as best as possible. And in longitudinal models, this includes predictors as well as the other outcomes from the person. So those things help to satisfy the missing at random assumption that full information maximum likelihood or multiple imputation make, but you can never really be sure. So, where does that leave us? MLM handles missing data? Nope. It's the same rule as in any other model. The case has to be complete to be included. The difference is what constitutes a case. In our models, a case is an occasion within a person. A case is not a person. So it does delete incomplete cases. We haven't had to talk about this so far because odds are good you know what occasion it is if you have an outcome. The time variable is almost never missing. So as a predictor, we don't need to worry about that one the same way that we need to worry about other predictors being missing. And so if you're not going to do anything extra to address the presence of missing predictors in your model, what I would advise you to do is to pre-select your sample to only those cases that are going to be included in all the models, the cases that are complete. The reason to do that is to keep your sample constant as you add things in and out. -2 log likelihood is literally, it's -2 times the sum of each person's height So if you drop people, those heights are not comparable. Same with AIC and BIC. So those fit statistics that you use to decide what things to keep in your model are only valid to compare if it's the exact same sample. So if you drop cases by adding a predictor where the people who are missing the predictor are out of the model, your -2 log likelihood will decrease just for that reason.
So would that harm the generalizability of the
Absolutely. Absolutely it will. So in terms of what you're, come on, wake up. So yes, let me, absolutely it will. I'll elaborate on that in just a second. So let's practice. So if this is my data set here, here's the multivariate wide version, here's my longitudinal stacked or long version. Which rows go in the model if I just have time? Well, time is complete. DV is missing for this person, so all the rows but 7. What if I have a time varying predictor 2? Well, first 3 are complete, I get those, not 4. I get to keep 5, not 6, not 7, and I get to keep 8. What if I add the person level predictor? Rut row. If this person is missing a time invariant person level predictor, it is missing for all of their occasions and they're gone. That is listwise deletion. It's exactly what I just told you not to do. And does that harm your inferences, generalizability? Does your sample reflect some population less well because of the listwise deletion? Absolutely. Do you have less statistical power because you have less data? Absolutely. And it gets worse as you have more and more predictors in your model with different patterns of missingness. Come on. So what are you assuming then about the missing data? If you have time invariant predictors, you're assuming they're missing completely at random because those people are gone. You have no way of protecting your inferences because they're deleted from the model. The assumption behind time varying predictors is a little more squishy because some of them may be in the model for other occasions. So in that sense, it's kind of like the MAR assumption that we make for missing outcomes because the other outcomes from the person are in the model. But given that it's still a conditional model in which those cases are gone, it's somewhere between MAR and MCAR. I talked to Craig Enders about this, one of the people whose research area is missing data, and that was his characterization of time varying predictors. It's somewhere between MCAR and MAR probably in practice. So what do you do about it, right? You can't fill in one value, single imputation, and you want to try not to drop cases if you don't have to. So there's 2 solutions. Each of them has potential downfalls. And so this is the point at which somebody typically raises their hand and says, but what about structural equation modeling? You can have missing data in structural equation models because FIML, it handles it. Sort of. What happens in structural equation models, they do allow you to have missingness on predictors. However, the mechanism by which they do that is to bring the predictor into the likelihood as an outcome. So for instance, in M+, if you have a predictor and you mention any of its distributional properties, mean, variance, covariance, if you mention those as part of the model, you've brought that predictor into the model and it is functionally an outcome, even if it's not being predicted by anything. Because it's an outcome, you then have to make assumptions about its distribution, and the default is multivariate normal. So what if I have a time invariant predictor, something like gender, and I give you an option for man, woman, and somebody chooses not to answer? Can I bring gender into the likelihood in my model? Is gender ever going to be part of a multivariate normal distribution? Not if I've coded it with 2 values, right? So you're bringing it in and allowing missingness under an assumption that you can characterize it as an outcome. So you would have to pick the appropriate link function, appropriate conditional distribution in order to be able to use this trick. And early SEM programs and SEM textbooks used to have words in them that say, everything has to be normal to be included in these models. And that's because the software put everything in the likelihood. They didn't allow them to not be part of the likelihood, to be predictors that the likelihood is conditional on but not part of. So this first solution here is why I have never done a multiple imputation in my life. I will switch to a model that is multivariate. Unfortunately, ProcMixed can't do that. You do have to use some sort of multivariate software that's capable of doing structural equation modeling or multi-level structural equation modeling so that you can introduce the predictor as an outcome. So that's what I do. The other option is multiple imputation. And you would then impute data from a model, make a bunch of imputed data sets, run the same analysis model on all the data sets, and compile the results. And programs like M+ make this very easy to do. Where the problem comes in with this approach is that the analysis or the imputation model has to have everything in it that your analysis model would eventually have. So everything you're going to want to test for, you need to be able to sort of foreshadow that and make sure that it's represented in the imputation model. That includes random slopes. But you can't have a model that has every possible random slope without it blowing up. So the more modern approaches to this do an imputation process as part of a Bayesian estimation, where they would fill in a thing, put it in the chain, run the model, and it iterates through that. That's something that I'd like to learn more about, because I think a simultaneous analysis where you're dealing with the missing data and dealing with the model would be the most logical approach. But that's sort of, this is a new area of research and something that is still under development in terms of how to best go about doing that. So there really isn't one great answer for how to deal with missing predictors. Each method has its own potential limitations. Okay, questions? No questions from the audience? No? Are we sleeping? Oh. Okay. Bye-bye. Let you chill, little man. All right. So that's the bad news. So in all the examples I'm going to show you, I have pre-selected the data set so that I have people who are not missing the time invariant predictors. That's how I dealt with it. If you're only missing one or two people, okay, it's fine. If you have a lot more missingness, you'll have to think about more interesting ways of handling it. One thing that I have done, which isn't often mentioned in this context as a way of handling it, is to introduce the missingness as another category. So for instance, if I have someone who has male, female, and then didn't answer, I would treat it as a 3-category predictor. Or I would keep the people in who didn't answer and say that's what they picked. They picked not to answer. Because that's probably informative. Those people may be different in my outcome for reasons that I wouldn't have anticipated. So you can do piecewise types of effects when you have missingness. So for instance, if I asked for someone's annual income, I could make a dummy variable for whether or not they actually answered, and then put in a nested effect for the people who answered as to what the slope would be for the amount they gave me. Does that make sense? So then I keep the people who didn't answer. I put them into their own category, and I give them a model parameter. So there are more informative ways of handling missingness if you're not really sure what the problem is. And then if you do find things that people who didn't answer the question are different somehow, that makes it a lot more interesting than just getting rid of them or trying to impute your way out of the situation. So those are things that I would also think about as options for you. So assuming we don't have any missingness, time invariant predictors. That's what we're talking about here. Things that don't change over time or for which you've only measured it once. So even if you think it's going to change, if you don't have access to that information, you have to think of it as a level 2 time invariant person level predictor. Another type of time invariant predictor that you will see is something that represents a time variable at baseline. So for instance, if I have adults that are 80 to 100 at baseline and I follow them for 10 years, I would have age at baseline as a level 2 predictor. That would differentiate cross-sectional age differences. And then I would have time in the model to track longitudinal age changes. I would treat it as two different things. So age becomes time invariant because I've put it as a snapshot at one particular occasion. Come on, you can do it. We're going to center all of our predictors always so that the intercept stays reasonable and so that the main effects, when we have interactions, stay useful. You don't have to mean center them. You can pick some sort of meaningful constant, such as years of education. I would pick maybe 12 or 16, something like that. For grouping variables, I almost always do some sort of dummy coding. I hate effects coding, where they sum to 0 because then your intercept is not an actual person. So marginalizing across a categorical variable to me is less useful. I don't know why my mouse is going slow. So in terms of what these predictors can do, in within-person models of change, time invariant predictors adjust the growth curve. So here are 3 potential scenarios. Show them up here. On the left, let's say that x is a grouping variable where one group is in the dark blue line and one is the dotted line. If you have a main effect of x, that's a shift on the intercept. So that's one thing that time invariant predictors can do. If you put their main effect in the model, they're shifting the intercept. On the right here, this would be a shift in intercept combined with a shift in slope. So that would be a predictor by time interaction that creates different time slopes as a function of group. And in the middle here, I have an interaction with time. So there are different time slopes as a function of the level 2 predictor, but then I have main effect of x question mark. I have that to remind you that what the main effect of x, the time invariant predictor, is depends on where time 0 is. In the middle picture, if time 0 is at the beginning, it's possible that group does not predict intercept if intercept is here at the beginning. Right here. If time 0 is out here, then you may have a main effective group on the intercept. It becomes conditional, and you can ask the model what the effective group would be at any occasion. The one that's going to be given to you by default is the time 0 occasion. So when thinking about where to put time 0, these are the sorts of things that you want to keep in mind. I tend to put time 0 wherever the occasion is that I'm most interested in. Sometimes that's the end instead of the beginning. In models of fluctuation, all they have to do is adjust the mean level. So if there is no effective time, then there's nothing for a time invariant predictor to do with respect to that effective time. Other things that time invariant predictors can do that we're not going to get a chance to talk about is to predict heterogeneity of variance. These are known as location scale models. They're becoming more common. It's the idea that level 2 predictors can also predict differences in variance. So at level 2, for instance, let's say that I have something like change in height, and I have boys and girls. So if I think about putting gender in the model, if I put in a main effect of gender as a fixed effect, that main effect allows the boys and girls intercepts to differ by gender. If I put in gender by time as a fixed effect, that allows their time slopes to differ. It allows boys to grow faster or slower than girls. But then I could also put it in to the level 2 model for the variance such that I allow different G matrices, different sets of random effect variances and covariances by gender. That's another thing that gender can do. It can say that some types of people are more variable relative to each other than other types. Maybe the girls are more homogeneous, in addition to just being shorter. At level 1, you can also have differences as a function of a time invariant predictor. That is less common to do in models of change, but it's becoming increasingly common in models of fluctuation. So if you think about something like negative mood, right? You guys can think of people in your life that are like even keel, right? Like if you plotted their negative mood day to day, they'd just kind of be going along and nothing really phases them. You know people like that? Yeah, he does. He's like, I'm like that. And then there's people like me where it's like, you know, they're very volatile. So you can be sort of grumpy all the time but stable, happy all the time but stable, or you can be very volatile, where on average you're not grumpy and not happy, but it just depends on the day. The extent to which a predictor is related to this volatility, this inconsistency, that means that you're allowing a different level 1 residual variance as a function of the level 2 predictor. Differences in fluctuation. The default assumption of these models is that everybody shares the same residual variance, but that's a testable hypothesis. And you can introduce predictors of the amount of variance at its level or lower. So again, those are called location scale models. I have some examples of fitting those in chapters 7 and 8 in the book, the ends of the chapters. M+ version 8 also has implemented this, and Don Hedeker is the man on these models. He has written a whole series of programs, Supermix, MixReg, Mix whatever, that do this. So that's where I would go if you're interested in that kind of stuff. Yeah, super cool, buddy. Questions so far? No? All right. The one thing that level 2 predictors cannot do, though, is have random effects. So if you only have 2 levels, a level 2 person level predictor cannot have a random effect. It can only have a fixed effect. And I've tried to demonstrate here why that is the case. So for a level 1 predictor like time, or anything that's measured repeatedly, you would have different values for each person through which you could give each person their own slope. So we could say that this pink person here doesn't grow as quickly as the blue person. Each person can have their own slope. But if I were to put gender into the model, if gender is time invariant, each person has only one value. You cannot draw a line through one dot. So level 2 predictors only can have fixed effects. Now where that could change is in level 3 models. Let's say that kids are growing longitudinally and that they come from different schools. A fixed effect of gender would look at the mean outcome difference between boys and girls. At level 2, that gender difference could vary over schools at level 3. But you can't have a random effect at its same level. It's only at the higher levels. So in everything that follows, we don't have to worry about testing random effects. It's all going to be fixed. All right. So here's an example of what it would look like if we had, say, a random quadratic model and we put in something like years of education as a continuous predictor. Education, if I know that I have 3 random effects, has 3 different roles it can play. So the model itself would look something like this. So I'm on slide 15 here. The level 1 model dictates the form of change that we're talking about. So this is a quadratic model. Beta 0 is the intercept. Beta 1 is the linear slope at time 0. Beta 2 is the quadratic slope. E is why are you off your line today? So if we go into each of these level 2 equations, because I have 3 betas at level 1, I have 3 level 2 equations, 1 for each beta. The fixed effects are in red, the random effects are in blue. Each of these level 2 equations is the same in structure. It starts off with the so-called intercept of the equation, and then there are predictors of each term. So if we do the first one, my computer is seriously lagging today. The deal is, so each person gets their own intercept according to this model. Previously, all we had was gamma 0, 0, which was the fixed intercept, and we said that was on average, right? And then U0 is how far off yours is from that. Well, now we are conditioning the fixed intercept also on education. So I've introduced gamma 01, which is a slope for the effect of education. So it is the main effect of education in this model. Because education is now a predictor, the intercept is not just conditional on time 0, but it's also conditional on when education is 0, which in this case is going to be 12 years. So my jumping off point then, gamma 0, 0, that's my expected outcome at time 0 for someone who went to high school. Gamma 01 is the change in the intercept per year of education. So now, anybody who has the same education level as somebody else has the same predicted intercept. U0 is then how far off your intercept still is after controlling for education. It's differences in intercept among people with the same education level. It's why else is your intercept different? Well, I don't know. It's not education because that's already in there. So in terms of effect size, when we put gamma 01, the main effect of education in the model, we would look to the difference in U0 to see how much variance we have explained relative to the model without education. And we would compute a pseudo R-square to describe how much intercept variance specifically the main effect of education has accounted for. Next line. Same idea, different term at level 1. Beta 1 is how each person gets their own linear time slope. It starts off with the average time slope, but because we have this education predictor in this level 2 equation, this gamma 10 is the time slope specifically not only at time 0 because of the quadratic, but also specific to education equals 12 years. Then gamma 11. Do you know what this is? It's an interaction. This is education by time. Gamma 11 is how the linear slope changes per unit education. So anybody who has the same education as someone else gets the same predicted linear time slope. U1 is then how far off the time slope still is for you after controlling for education. So if education matters in predicting why some people change more quickly, then U1 should have less variance in this model than before we put education in. So education by time should explain random linear time slope variance. Last but not least, same idea for the quadratic. Gamma 20 is the fixed quadratic. Because it's the highest order term with respect to time, it's not conditional on time. But it is conditional on education because education shows up in that equation. So it's the expected quadratic term when education is 12. Yeah. Gamma 21 then is how the quadratic term differs per year of education. In other words, gamma 2-1 is a three-way interaction. Education by time by time. If education matters in predicting why some people have greater rates of acceleration, then you too should have less variance than in the previous model without education. Yeah. He's like, I get it. So because I knew from my previous analyses that I had three potential ways that people differ from each other, education has three potential roles it can play. So that's what I mean when I say you have to get time right first, because it dictates what else is possible. Now in this model, what's going to happen to E variance at level 1? Any guesses? Does it stay the same? Does it go up? Does it go down?
Down?
Does it go down after I add education in? Mm-mm.
I thought you kicked me out.
Yeah, E would go down when we add fixed effects of time and time squared. But E variance is why are you off your line today? So if I have a PhD, I have a PhD every day. That can't explain why I'm doing worse than predicted today relative to tomorrow. Instead, what kinds of things would explain why are you off your line today? Hypothetically, pulling an all-nighter, right? Might that be a reason why you would be doing worse than predicted today than any other day? Hypothetically, right? Things that are transient, things that are time varying, that's what captures E variance. Things that are time constant, that captures between person time constant sources of variation. Mm-hmm.
So it should stay relatively the same.
It will stay the same. It might wiggle a little bit based on unbalance in the data, but it should stay the same. So in terms of baselines, when you're reporting in a paper, the model that doesn't have any predictors in it, that just has all of the fixed and random effects of time that you need to handle the time part, that is now like your new baseline. That's what's known as your unconditional model of change. That would be like the first model in a table, because that original model without education would have as much random effect variance as there is to be predicted. Then you see how it goes down as you add predictors of each type. So this slide, I think, helps illustrate the logic of the subscripts. The first place in each subscript refers to which level 1 beta you're talking about. So in the beta 0 line, hey, come back, all the terms start with 0, because these all refer to beta 0. In the beta 1 line, all the terms start with 1. In beta 2, they all start with 2. The second digit in the subscript then picks up how many predictors in you are in the level 2 model. So right here, this is gamma 01, because this is the first predictor of beta 0. Likewise, this is gamma 11, because this is the first predictor of beta 1. And gamma 21 is the first predictor of beta 2. What if I added another time invariant predictor to the beta 0 line? What would its subscript be? 02, 02, 03, 04, 05. And then down here, if I added it to the linear time slope line, 1, 2, exactly. So it's kind of like a grid system. Anytime that you see a coefficient that has digits in both places, it has to be an interaction of some kind. That's the only way you can get numbers in both spots.
first subscript shows the degree of the polynomial, right?
Say that again?
The first subscript under the, the 0, 1, 2, it shows the degree of the polynomial, right?
Yes, it's more generally, it's which beta it's referring to.
Yeah.
In this case, it's degree of the polynomial, but like if we have a piecewise model where this is slope 1 and this is slope 2,
I just asked
then, yep, exactly. You will sometimes see people refer to these fixed effects differently, where they talk about them as like the intercept of the intercept and the intercept of the slope. Have you heard those terms before? That sometimes shows up in education. That's an HLM convention. I hate it, but I can try to explain it because you may come across it. So if you look at each of these level 2 equations, the fixed effect that's at the start is like the jumping off point for the equation. In that sense, you can think of each of these as intercepts. Because if you had nothing else in the model, these would be the mean for that term, the same way that the intercept is the grand mean if you have an empty model. And so gamma 0, 0 is the intercept of the intercept. Gamma 1, 0 is the intercept of the linear slope. Gamma 2, 0 is the intercept of the quadratic slope. So sometimes you will see tables where they have like a heading that will say like linear time slope, and then sub rows where the first one is intercept. That's what they're talking about, is this fixed time slope here, is the intercept of the linear time slope equation. And so then you get into the logical possibilities of gamma 01 here is the slope of the intercept, and that means gamma 11 is the slope of the slope. And I'm just like, no, that's not helpful. So it gets really tricky to keep things straight if you just use the word slope. How many slopes do I have on this page? 5. I can't just say the slope, right? That's not specific enough. And the slope of the slope is also not specific enough because I have 2 of those. So linear time slope. By the way, this is also a linear education slope. Could I put in a quadratic effect of education? Sure. It would be 02, 12, 22. So all of the ways of modeling nonlinear effects that we talked about for time, those aren't just specific to time, they can work for any continuous predictor. So it's still a linear slope. It's the linear slope of education, as opposed to the linear slope of time, as opposed to the quadratic slope of time. So to be the most specific, gamma 2,1 is the linear effect of education on the quadratic slope for time. Right? That is specific. So that's the technical definition, and I would say something like more educated people are more bendy. That would be the lay term version. So these 2 terms right here, this 1,1 and 2,1, these are known as cross-level interactions because they involve, and I'll write it as a composite here, a level 1 predictor interacting with a level 2 predictor. So in these models, you can have level 1 predictors and level 2 predictors. You can have cross-level interactions. You can also have a level 1 interaction, which we do have one of those, time squared. That is an interaction between 2 level 1 variables. It's a level 1 interaction. We could also have a level 2 interaction if education interacted with another level 2 predictor. So we can have main effects and interactions at each level as well as across levels. And what each effect has to do depends on how many random effects are in the model. So let me show you this idea here. So pseudo R squared for each of these terms. The general rule is that if you start with an unconditional model like what's right here, this is as much random effect variance as there is in each term. This is all the unexplained variation between persons in intercept, linear time slope, and quadratic time slope. So our job then is to figure out why each person needs their own random effect, and we put in level 2 predictors. So in general, the level 2 predictor's job in the model is to explain the random effect variance that's in its level 2 equation. So the main effect of education explains random intercept variance. Education by time explains random time slope variance. Education by time squared explains random quadratic time slope variance. And it's all neat and tidy, right? Now what if you end up with something different in terms of your unconditional model of time? Come on. What if you end up with something like this on the right instead? Let's say that you go through all the steps that we talked about at the beginning of class, testing fixed and random effects of time, and you end up with a model that only has a fixed quadratic effect of time and a random intercept. That could happen. It's especially likely to happen if people don't change differently, or if you don't have a lot of people and you don't have a lot of power to detect those random slope variances. Then the question is it still acceptable to put a level 2 predictor in each of these level 2 equations? Yeah, I know. This is an area of research that I'm interested in part because I've had reviewers yell at me for trying to do this. So there's two sides to this argument. Some people would say no, and they would say it like that, capital no. It's like, let me get this straight. You don't have any differences in change, and you're going to try to predict that constant? How well does it go when you try to predict a constant, folks? Nah. If you don't have any differences, then what's the sense of putting in a predictor of those non-differences, right? That's stupid. It's stupid right now, as Huey would say. Hopefully he doesn't yell at you like that anytime soon. You heard that story from Jonathan? A few of you did? My son, when he was like 2.5, he learned the word stupid. He didn't know what it meant. One morning he's like, Mommy, you're stupid. And he's mad at me over something, like I probably wouldn't let him wear the same dirty shirt he wore the day before. He really gets angry when I try to put him in clean clothes sometimes. And then I'm like, buddy, that's not a nice word. I expected him to like say he was sorry. No, he doubled down. Mommy, you're stupid right now. Okay, well then, Daddy, your turn. So, these people would say, no, this is stupid right now. However, the alternative, which is in a couple other books that I was able to cite as well, the power to detect these cross-level interactions is likely higher than the power to detect their corresponding random effect variances. So you could be in a type 2 error situation where you thought you don't have any variance just because you don't have enough power to find it. So it still makes sense, in theory, that you could have these interactions have something to do. It's just a negligible source of variance that they have to attack. And so then the question is, are those interactions suspect? If you want to go this route, it requires learning a new vocabulary word. And that is the word systematically varying. Come on, you can do it. So, you know what fixed means, right? What does fixed mean? Constant. Everybody gets the same. Yes. Try to make him smile. Everybody gets the same. And what does random mean?
Changes arbitrarily.
Everybody gets their own of the effect, right? If you have a random variance around a fixed effect, that means each person is supposed to get their own deviation from the fixed effect. The variance across people is in a model parameter. The idea of systematically varying is a middle ground. It's not that it's random and everybody needs their own. It's that people need different ones systematically or deterministically as a function of a predictor. So for instance, maybe boys and girls need different slopes. But within gender, everybody gets the same slope. I would call that a systematically varying effect. The time slope varies systematically by gender, but not randomly otherwise. So here are the situations in which you might find yourself needing to describe this phenomenon. Let's say that you initially have a random time slope that's not significant, but the hypothesis that the study was designed to test is whether groups differ and change over time. If you end up with a non-significant group by time interaction, then I would say the linear time slope is indeed fixed. Everybody gets the same. It did not vary by group, and it does not vary randomly by person. If that group by time slope were to be significant, that's when I would pick up this new term. Each group needs a different time slope. Otherwise, that interaction would not be significant. But within groups, everybody gets the same. Seems perfectly reasonable, right? You could also have a random time slope be initially significant, but then go away after you add group by time. Go to 0 or close to it. In that case, hooray for you! Think about it. If I have a random linear time slope variance, and I put group by time in the model to explain it, and the random time slope variance goes away, hooray! That means I have explained all the reasons why people needed their own slopes. It's because of group and nothing else. I win. R square for the slope of 100%. If I had a significant group effect on the time slope, and the time slope stays random, then it's random either way. And I would say yes, each group needs a different time slope, and we still have unaccounted for time slope variation within groups after controlling for groups. That would be random. So to me, because these things seem reasonable, I would say I fall into the yes camp in terms of whether or not you can fit a model that looks like this. The catch is just making sure that you try your best not to make a type 2 error, and that if there is a random slope that you can find or is sizable enough to care, that you keep it in the model. So the order of operations is very important. Before you put in these cross-level interactions, you would always want to test whether the random slope variance they were supposed to predict should be there. Always build the random part first and then the stuff that's supposed to explain it. Otherwise, you may be at risk for higher type 1 errors. I have a simulation study that I've been working on to look at this issue. It's a paper that's under revision right now, and I did a study that suggested that if you pay attention to slope reliability, there's a formula by which you can compute it. We talked about this earlier in the semester. If you make the decision to keep a random slope that has reliability of about 0.2 or higher, you can mitigate your chance of type 2 error in this case. So making a decision based on effect size rather than significance is something to think about when you have very small samples, such as we looked at in this paper. So practically speaking, that is what I would recommend. All right. How are we doing? We're still awake? Yeah, we're all still awake. Do you have any questions before we adjourn? No? All right, then have a good day, a good weekend, and we will see you on Tuesday. Let me know if you have any questions on homework 6, and I will fix homework 7's starter SAS code. Hi.
Smiling.
Yes, Mommy, I cannot get this to work. Exit and show. My keyboard is like deciding not to work. There we go. Now we can stop.